Hi everyone, and welcome back to this new video about transient response of first order circuits. This is our example 4. We have our RL circuit with independent voltage source connected to a series combination of two resistors and one inductor. There is also a switch across the resistor R1, which will be closed at time equals 0. It is now at the moment open. What we like to know is the expression for the inductor current IL as a function of time for time greater than 0. So what we do is we would like to know the expression for the IL in general form, and then we will try to figure out what the parameters are in the formula. So the IL, the inductor current, is, as discussed in the previous examples also, is IL steady state plus the IL initially minus IL steady state between the parentheses times e to the power minus t divided by tau. So what you see, again, what we have discussed in the previous 3 examples, we need 3 parameters: the steady state value, the initial value, and the time constant. Okay, for the initial value, you look at the circuit without the change. So this circuit is still without closing this the switch. So the switch is still open. So what you have is actually the VM voltage source, two resistors in series, and the inductor. Since we know, and since we assume that the circuit is running for a long time, the inductor is assumed to be a short circuit if you wait for a long time. So for the condition for time less than 0 seconds, you can say that IL or the circuit behave like this. We can draw it again to make the situation clear. So actually what you have is an inductor that is modeled like a short circuit, and there is a current flowing here for this case. So that current IL will be, of course, Vm divided by the series combination of the R1 and R2. So we will add them up. That's 12 divided by 100 plus 200, and that will be calculated 40 milliamps. This is our initial condition for the inductor, initial condition of initial value. Okay, so that's actually one of the parameters. So we would like to know what the final value is, or the steady state value. Then you need to know that there is a change in the circuit. So the switch is closed, so this will be short circuit, so the R1 is out of the picture. Again, we look at the new circuit and we assume that the circuit is running for a long time, so the inductor is again assumed as a short circuit. So what we can say, if we write it down, for time greater than 0, and again we assume we will wait for a long time, then the circuit will be like this. So it is almost the same as the previous one, only R1 is out of the picture, and we have it like this, and this will be IL. I see there is a mistake here in the writing, so it will be R2, but that doesn't matter. Okay, so what we have is the IL for the steady state. So that's the notation for IL steady state. That will be Vm divided by R2. So it's the exact same situation, only one resistor less, so that will be 12 divided by 200. So that will be 60 milliamps. And this will be our steady state value. Steady state value. Alright, so that means only the time constant. For the time constant, again, I will like to remind you, you look at the circuit after the change is made. So the switch is closed, you look at the circuit in that situation. So I will draw it again. to make the situation clear. So time constant, that's the next step. So what we have is actually the following. We have a circuit. R1 is again out of the picture, so we have only the R2. There is the inductor. And what we always say is, if you have a calculation for the resistors, so we need that for the time constant, because you know the time constant for the RL circuit will be the inductor divided by the Thevenin resistance. So the Thevenin resistance is actually the resistance seen by the terminals of the inductor. So if you have a VM, that is the voltage source, so all of the independent sources will be, of course, deleted or will be put out. So that will be, this one will be short circuit. So you will disable all of the independent sources. That will create a short circuit here. And in this case, the situation is very easy because the resistance seen by the inductor is just R2. So the R Thevenin is R2, and that is 200 ohms. That will bring us to tau is equal to R2 times, so I mean L divided by R2. So that will mean 0.005 divided by 200. Now if you calculate it, you will get 25 microseconds. 25 microseconds. Okay, now I will use all of these information to fill this formula, because I need these three parameters to fill this in, and then I will be done with the example. Okay, then what we get? I get IL as a function of time is IL at infinity, that will be 0.06 plus 0.04 minus, that will be initial condition 0.06, and I will do that times e to the power minus t divided by 25 micro. Okay, I will simplify this to make it easy read. So 0.06 minus 0.02 e to the power minus 4 times 10 to the power 4 t, and that will be in amps. So if you want, you can always go to the milliamps, so you can always say, okay, I would like to work in milliamps. That will maybe easy for future calculations. So 60 minus 20 e to the power minus 4 times 10 to the power 4 t milliamps. Remember, I just calculate with multiply everything by 1000, and don't use this, of course, with 1000. That's actually the exponent, so that will be the same. That's actually the example 4 for transient response, and in this case for an RL circuit. And that's actually these are the steps we follow to come up to this formula for this expression. I hope it will clarify the situation in more detail. So there are 4 examples at the moment. I will, of course, work on more examples for more topics. So keep in touch and share this video. And of course, don't forget to like. And if you don't, so subscribe to the channel. I will see you next time, and good luck. Thank you very much for your attention.